Buon pomeriggio, or good afternoon, everyone. I want to show my Italian. I promise not to pull anyone's tooth out like the first lecture.
Is necessary for the registration?
You can't hear it? Oh, I can't work with that. I have a very strong voice.
Okay.
Believe me, I never use it, even when I have 200 students.
Put the microphone to
What
the
I would like to talk about is a process that most people probably are not aware of, and I would like to give a very short review. The Autofrettage process was invented by a French captain of the artillery in 1907. The idea behind it was to improve the pressure in gun barrels so that you get a better range or a higher kinetic energy, depends if you are a tank officer or an artillery officer. This gentleman was very smart, Jacob, but unfortunately the first to use this idea were the Germans during World War I. In this method, gun barrels, and here we speak about cylinders in the military term, to spherical pressure vessels, you put a very high pressure inside, you create yielding of the wall of the cylinder, of part of it, of all of it, and then when you remove the pressure back, you are left with residual stresses inside the cylinder. They are compressive at the inner part of the cylinder, and they are tensile at the outer part, because there are no free lunches, unfortunately, not even at this conference. Now, the presence of autofrettage has two advantages. The one, which was the initial imagination of that artillery officer, is to allow an increase of the vessel internal pressure, which is evidently clear. But with the years, we found out that this is a second advantage due to the fact that the stresses at the inner portion, which is the place where cracks start or initiate, if you have compressive stresses, this will decrease the susceptibility of cracking. So it is better for fatigue life, it is better for firing power, so everybody should be very happy, except it is very expensive to do. So, spherical pressure. Spherical pressure vessels are used a lot in industry. They have a big advantage because they sustain a much higher pressure than cylindrical pressure vessels. They are more complicated to be manufactured, and the problem is that nobody ever gave any attention to the question whether we can put autofrettage in spherical pressure vessel. To the best of my knowledge, and I have a little bit experience, nobody has ever used autofrettage in spherical pressure vessels. And the question was, is it feasible, is it good in pressure vessels, and how much does it affect the fatigue life of such a pressure vessel? And you should be very much aware, because we live in a very nice world where you have every morning another attack, here or there or somewhere, and police all over the world are using particular pressure vessels in order to detonate bombs that they find. They find a bomb, they put it into a big spherical pressure vessel, and they detonate it. Now, if you look at them in the United States, every police station has such a big sphere, which is very heavy, and it would be very interesting to find out if autofrettage would help, first of all, detonate much higher pressures. Secondly, will it sustain a much longer fatigue life? Very interesting. So, we went further on, and what we are trying to learn in this case, I'll put them all three, is, on the one hand, what is the stress intensity factor at a crack, at an inner crack, which results from the internal pressure. Then we have a positive stress intensity factor. By the way, each sign is negative, which is due to the residual stresses due to autofrettage. And finally, the combined stress intensity factor, which will dictate the fatigue life of the vessel. So in order to do so, we try to calculate many K1As and K1Ds, of course, and I'm just giving a very brief description of the cracks. Cracks in spherical pressure vessels are very different than in cylinders because the curved part of the vessel inside, and we have lunar cracks, which are circular, if you want to call it, semi-elliptical in cylindrical cracks, and I would say something about ring cracks, because many people who want to analyze such a problem, they say, okay, we'll take a ring crack as an approximation and it is always very good. No, it is not. So let's go and see. Here are the three descriptions of the three configurations of the cracks. We did a finite element analysis, three-dimensional, and the residual stress field, which is the most important thing in this story, is applied to the finite element analysis using an equivalent temperature field. This is an old trick which is not known to everyone. In the case of autofrettage, it is possible to determine a particular temperature field that will create the same stresses as the residual field. And this will introduce into the analysis, because putting residual stresses into analysis of finite elements is not very simple. If there were civil engineers here, they would know what I'm talking about. Well, and then you calculate a J integral, which is embedded in the software. We are not geniuses, we use whatever exists. You have an element breakdown, and unlike in the case of the tooth that was described here beforehand, in this three-dimensional analysis, we are using particular elements which give you the right singularity on the crack front, the R to minus half. These are special wedges, and it is easy to have them in any finite element program. If you wish, I will tell you a little bit later on. So we have crack front curve with 20 node isoparametric elements collapsed to wedges, and then we have on top another 4 layers of 20 node isoparametric elements, and finally the rest of the model, in order to save computational time and memory, etc., is with 10 node tetrahedrons. Okay, we are now ready to show some. Of course, we start with small elements near the crack front, and bigger as we go far away, in order to keep the accuracy to be reasonable. And the autofrettage model is the greatest secret. Autofrettage was for the first time analyzed analytically by Hill. He's a British gentleman. He did a beautiful model, which is not realistic because it's beautiful. This model has been used for many years. Now, the latest model was developed by a student of mine and myself in 2007, which is very realistic. When you look at the two models, they seem to be almost the same thing. The problem is that the most important part is at this point, at the inner surface. And here you can see that there is a big gap between the two models. So if you use Hill's models, it is extremely optimistic. And we are realistic people, not optimistic. So we've used our residual stress field. And we used it with, as I said, equivalent temperature field. And we solved many cases. I'll put them all just to show you how much work we did. And we used it for two basic configuration cracks that are radial, many radial cracks, because many spherical pressure vessels are manufactured from petals, and in between the petals you can have cracks. And also for coplanar cracks, namely you have two hemispheres weld together one way or another, and on the equatorial plane you can have more than one crack. And altogether in this case we solved just 300 cases, three-dimensional one. Excellent student, Matan, who did the work. He deserves all the credit. I was just thanking him. Let me see some results. They are very different from what is happening in a cylinder. For example, in a relatively thin spherical pressure vessel, if you have radial cracks, the number of cracks that you have around almost has no influence, because a very narrow band. If you take the same configuration but with a thick sphere, look what is happening. Two interesting things here. First of all, as the number of cracks increases, we have a decrease in the stress intensity factor. Secondly, the one crack is not the most critical crack. By the way, people thought for many years that one crack, sometimes two cracks are the most critical situation. This is not true. Sometimes it is 4 cracks and even 8 cracks. It can happen. In this case, it is 4 cracks. If we look now at the stress intensity factor due to autofrettage, in the vessel. In this case, for a coplanar crack array, we can see as the density increases, of course, the stress intensity factor increase because cracks are becoming closer and closer. Interestingly, again, another thing that people are convinced of it is where is the maximum stress intensity factor? You can see that in this case, it is at 90 degrees, which is the deepest point of the crack. This is not always the case. Sometimes it is at the surface where the crack meets the internal surface, and I'll show you immediately just to convince you. You can see here that here you have two maxima, and there you have two maxima, so it depends on the particular geometry of the problem. So never say again that the inner point is the most critical or the intersection point. One of them is the most critical. Ring cracks. Ring cracks have been used when you have many cracks on a plane. We said, okay, make an approximation, say that this is one ring crack, and this will be always good. No, it is not. So here you have a ring crack, distribution of the stress intensity factor due to autofrettage, and you see how it behaves with the thickness of the sphere. Now, in this case, we see on this particular case that the solution for the ring crack is higher than the solution for the coplanar cracks, which means that the ring crack is a good upper bound to the solution. But you change a little bit the information, and look what happens. Here you have a case in which the coplanar cracks have a much higher stress intensity factor than the ring crack. As a result, and this is good for the people who are doing the analysis, you have to come to me to buy the solution for your particular case. Now, what is the impact of autofrettage on the fatigue life of such a sphere? We just made the first approximation using Paris law, and this is the answer. You can prolong by 25 times the fatigue life of such a pressure vessel, even if this number is not accurate, and it is not accurate. It's only an approximation. Even if it's 20 times, it's a good job, a good business. Let me just say one thing. Actually what we did, we analyzed the interaction between cracks in various configurations of radial and coplanar cracks, of all configurations that have been described here, and we saw the variation of the stress intensity factor due to autofrettage. I didn't show the one due to internal pressure because this is considered simple. It's not so simple either. And we saw that density of cracks has a different effect on radial cracks as coplanar cracks. In radial cracks, it decreases the stress intensity factor. In coplanar cracks, it increases the stress intensity factor. And finally, the commonly accepted approach that the ring case is the upper limit to the problem is not always the case, to be delicate. Not always the case. Thank you.